Greetings, everyone. I'm Akash and my friend Aditya have created a service that uses LLMSherpa and Graph-Augmented RAG to effectively answer to the queries of users using the Graph knowledge base. We are using two cloud technologies in our project. The first one is the Neo4j Aura DB, and the second one is AWS EC2. So the project covers an end-to-end pipeline from parsing and ingesting PDF documents and then creating a knowledge graph for given natural language questions. We are using OpenAI embedding API to capture the semantic meaning of the content. Also, Neo4j Aura DB, a cloud service for the knowledge graph, and we are deploying the application on AWS EC2 instance. We have also created another model which summarizes the data. We are in the industry of academia, so for data, we chose the publicly available research papers. So what we did was we created a model which summarized the research documents or the research papers. But then to improve the data retrieval process, we decided to maintain a graph knowledge database where the data would be well maintained in a proper structured format and would be easier for the retrieval and also would give accurate answers. So these are our solution components. So the first one is LLMSherpa. It's a PDF document parser and used for content extraction. It is a Python library that helps in maintaining a hierarchical layout for the information that is extracted from the document. It divides the information into chunks, sentences, and tables so that the structure of the document is well maintained. The next one is the Neo4j Aura DB that we are using for the graph knowledge base. So this is a fully managed cloud service provided by Neo4j. It offers the popular graph database as a cloud-based solution. It's designed to provide users with the powerful capabilities of the Neo4j graph database without the complexity of managing the infrastructure. The next one is the GenAI stack, which is used for fast prototyping. This GenAI stack is a pre-built development environment created by Neo4j in collaboration with Docker, LangChain, and Olama. In our project, we'll only be using the LangChain component for the development of our service. The last one is the OpenAI model that we are using to get the embeddings. So we have purchased the OpenAI API key for the project to get the embeddings of the data that we are going to use to feed into our knowledge base. So this is the RAG pipeline, basically the architecture of the service. So as we are in the industry of academia, so we have used the publicly available research papers as our data set. So these PDF documents are those research papers. We have a bundle of research papers that we have used. So these documents are fed to the LLMSherpa, which extracts information from it in a very structured format that is divided into chunks, sections, and tables. Then these chunk sections and table are fed to the OpenAI model, that is a GPT 3.5, to generate the embeddings. Then these embeddings are passed on to Neo4j for the formation of a knowledge-based graph, which will be having all the metadata. So the metadata is in the form of nodes, and these nodes are connected by relationships, which I'll be showing you. So we are getting all the input from LLMSherpa in a proper structured format. That is why all the information that is stored in Neo4j is very structured. So this will help in the effective retrieval of information from the graph database. So whenever the user has a query, he sends a query, and this query is converted into embeddings first by the OpenAI model, which is then given to the graph knowledge database, that is the Neo4j. So here the embeddings are converted into Cipher language, which is the language that Neo4j uses to manage its database, and then all the information that is required to answer the question is retrieved effectively and then sent back to the OpenAI model, which converts the embedding language back to the natural language so that the user can read it. This is the graph schema. You can see several nodes like question, answer, embedding, table, document, chunk, and section. The edges are the relationships. So whenever a question is asked by the user, the queries flow through these nodes and then an answer is generated. and then given to the user. The schema is actually given by the Neo4j database, which we had created. We'll be showing you that in some time. Now I would ask my friend Aditya to proceed with the demo.
Thank you, Akash. So now I'll be starting off with the demonstration of our project. So now we'll look at the first part of our code, and that is our PDF ingestion code. So as Akash already said, we are focusing more on the research papers. Yeah, so here we are looking at the first part of our code, and that is our PDF ingestion code. So from this, we have to start off with LLM Sherpa. Now, LLM Sherpa doesn't really have an active server anymore. So you have to come over to the NLM ingester page on GitHub, and you need to start this Java Tika server. After which, you need to run the Python daemon for the ingester, and you need to pull the Docker image and then start it on port 5010. That will generate the LLM Sherpa URL, which you can plug in here, along with all the papers or the documents that you would like to divide into chunks. So the first part of the code that we're looking at, we are basically dividing, or we are basically defining the constraints and the schema of the Neo4j Aura DB. So we are using the Neo4j Aura DB as it is a graph database. So using this, we define the relations and the nodes. After defining this, we initialize the Neo4j database, and then we pass through all the PDF files to the LLM Sherpa API. The LLM Sherpa API will then divide this document into multiple sections, and then within the sections into multiple chunks. So after this, we come to the second part of the code. So you plug in the OpenAI key and you join your Neo4j database to the code, and you basically go through all of the chunks in the database of in your Neo4j database. So that returns multiple embeddings. So the model that we selected is the text embedding ADA002. That is a embedding model from OpenAI, one of the best state-of-the-art models. So basically, we get the embedding for all of the chunks inside of our Neo4j database, which was divided by our LLM Sherpa UI, API. So now coming to the Neo4j Aura DB. So this is the interface provided by Neo4j to visualize the graph database that we have just created. So we have multiple nodes that we have already defined. So currently, we don't have to be worried about the question and answer. We haven't reached that part yet, but you can look at all the relations that have already been defined. So after this, the next part of our project was to actually deploy this on a cloud interface so that it could be used widely and could be provided as a web service. So as you can see here, we are running this on our instance 2 on Neo4j Aura DB. We actually deployed this on the AWS Asia Pacific Mumbai servers. Okay, so in case instead of deploying on the AWS EC2 cloud, you want to deploy this locally, you can also pull the image from the Docker hub onto your local machine and run these small containers that are present inside of the image. Once you do so, there will be a local URL generated which you'll be able to visit on your local browser instead of actually deploying this on AWS. So coming to our AWS console. So as we can see here, as I expand this, you can see all the statistics that are visible here. So upon every API call, there is a fetch from the EC2 server, and AWS keeps on providing the Neo4j Aura DB, the data inside of that live. So now we have entered our virtual machine that AWS provides, and we'll start executing some commands to actually get the front end working. So after running some commands, AWS gives us some URLs to actually visit. That is actually hosted on their servers. Okay, so now after connecting to our EC2 instance, the virtual machine provided by AWS on their external URL, let's try to explore what the application actually can do. So let's put in a simple query. So as you can see, when the RAG was disabled, at this point in time, there was no fetch made to the Neo4j DB, and it was just a generic prompt that was given to the OpenAI GPT 3.5 model, which you are utilizing right now. So as you can see here, once the RAG framework was enabled, the GPT 3.5 model that we gave the prompt to is correctly able to give the answer to the question of what CAM process measurement is. Along with that, it is also able to pinpoint the source. So with this, we can clearly see that traversing the graph to actually receive the correct output clearly works and is quite fast and efficient compared to normal RAG searches. So currently, we are utilizing the GPT 3.5 architecture, which is a more generic or a more general purpose model. But we as a group also fine-tuned a very specific model, which is used for the task of summarization. So we can look at the code. So the model which we have fine-tuned is the Google T5 small model, which was fine-tuned on an A100 GPU with high RAM instance. That is the 40 GB instance using the IaaS service provided by Collab. To get a further look at this, we have uploaded the IPYNB file on our GitHub page. This model currently is able to beat other state-of-the-art models found in the task summarization of research papers, but we did not utilize this model due to it being only limited for task summarization. Therefore, going with the GPT 3.5 model. So now we'll be moving on. So now we are trying to look at the comparison in terms of numerical values between a normal RAG and a knowledge graph-based graph RAG. So we're looking at two methods here, and we have taken two benchmarking scores. So that is the Roach 2 and the BERT score. So Roach 2 is basically a bigram metric, which basically compares two words, and if both of the words are consecutively appearing, the model is given a higher score, or the framework is given a higher score compared to the other. So we have three individual metrics in this, that is precision, recall, F1. Again, depending on the true positive, false positive, true negative, and false negative, the scores have been applied. So here we can see between Roche 2 and BERT score, the only place where RAG is able to beat the knowledge graph framework is in the Roche 2 precision category. Everywhere else, the knowledge graph is able to beat RAG. So BERT score actually measures what is the semantic meaning of a certain paragraph or a sentence. And we can clearly see that the knowledge graph framework gives a much better output compared to the RAG method, beating it across precision, recall, and F1 score, all three, by a significant margin, showing that the knowledge graph method is a much better method compared to RAG. So let's look at the future work that's possible from this point. So firstly, we can also integrate more than one modes. Right now, we are considering only textual data, but we can also include things like images, diagrams, which are commonly found in research papers, into our knowledge base. We can also rank multiple types of nodes based on their importance, and the more important nodes will clearly be given priority while retrieving data. We can also incorporate deep learning techniques like graph neural networks, which will allow us to re-rank these nodes and give us better reasoning and retrieving capabilities. We can also expand the user interface, which is currently quite limited on the back end. We can advance this using advanced filtering, query history, and multi-document handling. That's it from our group. Thank you very much.